Good evening. This is Donna Blumquist, librarian at the LaSalle Public Library. Welcome to tonight's program, Hidden Universe, James Webb Space Telescope. Before we begin, just a few programming reminders. Tomorrow, Tuesday, July 12th at 6 p.m. Central Time, the library will present Greed in the Gilded Age, presented by author and historian William Hazelgrove. Mr. Hazelgrove will discuss his new nonfiction book, Greed in the Gilded Age, The Brilliant Con of Cassie Chadwick. On Tuesday, July 19th at 6 p.m. Central Time, Scott Pelican, one of tonight's presenters, will be back to present Godspeed, John Glenn, a program commemorating John Glenn's historic flight in 1962, when he became the first American to orbit the Earth. Scott is a NASA Solar System ambassador. And on July 26th at 6 p.m. Central Time, movie fans should plan to join us for the Hollywood blockbuster, How Steven Spielberg and George Lucas Changed the Movies. Brian Rose, professor emeritus at Fordham University, will present 4 decades of filmmaking by Steven Spielberg and George Lucas. The genius of these two filmmakers, the storytelling, and the special effects changed movies forever. Don't miss this unique presentation. As always, all programming with the LaSalle Public Library is free and open to the public. It is also shareable, so please feel free to pass the information on to others. And now I'll close my mic and turn the program over to our 2 NASA Solar System ambassadors, James Joel Napper and Scott Pelican, so that we can all gain a better understanding of the scientific significance of what the James Webb Space Telescope will show the world and why it matters. As always, please post your questions in the chat. We want to hear from you. Joel, Scott, welcome.
Hello.
Welcome. Hello, everyone. Can you hear me, Donna?
We can.
All right. Joel, how are you?
I'm doing well. Scott, do you want to introduce yourself?
I will. My name is Scott Pelican from LaSalle, Illinois, and I am a NASA Solar System ambassador. This is my first year in this role, and I actually have the LaSalle Public Library and Joel here to thank you very much for me being in this position. It was a program that Joel put on about women in space back when the pandemic started, roughly, that I signed on to, and it was, of course, wonderful. And at that time, at the end of the meeting, Joel mentioned a little bit about the Solar System Ambassador Program and how you could join, and I gave it a shot because of my lifelong love affair with all things space and NASA. Believe it or not, I was rejected the first time I tried, but I stuck to it, tried it again, one more time, and I'm sure they figured we're never going to get this guy off of our back. So they let me join, and it's been a wonderful experience. I've had such a great response, and again, Don has been so helpful to me down at the library, and of course Joel has too, and helped so much with putting this program together. So this is really an exciting time for NASA and space exploration, not just with the James Webb, but this alone, as we're going to talk about tonight, is something that is just simply amazing. And who knows what we'll see. And I think our program is going to proceed where we'll let Joel tell us a little bit about himself, and then Joel will kick it off from there, and then I'll chime in a little bit later. So Joel, it's all yours.
Thanks, Scott. It was a pleasure working with Scott on this presentation. We hope to share with you some of the exciting things about this amazing observatory that has successfully reached its destination and is getting ready to actually start doing science for us. So we're happy to speak with you tonight. Wish we were there in person. So hopefully in the future we'll be able to meet face to face again. But anyway, we're going to talk a little bit about the Webb. So we're going to talk about the origins of the James Webb Space Telescope, its major features, building and testing the telescope, that 30-day journey to the Lagrange point where it is now, the commissioning of the science instruments, and then the science. Well, so the James Webb Telescope grew out of the Hubble telescope. The Hubble telescope was our first great observatory that was launched by the space shuttle. Hubble telescope orbits around the Earth, and it's a good thing it did, because when the Hubble was launched and they commissioned it and they started looking at the pictures it was sending back, they discovered quickly that something was wrong. The testing they had done with the mirror had used some faulty equipment, and it was giving a blurred vision. So fortunately, the Hubble telescope was designed to be repaired and upgraded by the space shuttle, and they launched a flight soon after to replace the scientific instruments in the Hubble in order to make corrections for the mirror. And Hubble has gone on to really give us some stunning images of the universe these past over 20 years now. And the James Webb, when they were working on the updates for the Hubble, they put together a group to look at beyond Hubble. What kind of observatory would we want to have? And one of the thoughts was you put an observatory away from the Earth, out where it can not have to worry about where the position above the Earth. And you make it an infrared telescope where you can see more than what the Hubble can see. So they started working on the James Webb telescope. Originally, it was set to launch in the early 2000s, 2006, I believe. And the budget was $500 million, half $500 million for this James Webb telescope. But soon it became apparent that to be able to create a telescope with the capabilities that they wanted for the James Webb telescope, you weren't going to be able to get this thing launched in 2006, and it was going to cost a lot more than $500 million. So you could see the two images. You can see the Hubble and the Webb telescope. The Webb is much bigger than the Hubble. The primary mirror especially, where the Hubble's mirror was 7.9 feet in diameter. You can see they're compared to a human there. The mirror for the James Webb telescope is 21 feet across. So that's almost 3 feet, or 3 times the width of the Hubble telescope. So you're increasing the light gathering capability. That's one of the major difference. The other thing that's different between the Hubble and James Webb is that the James Webb is more of an infrared telescope. An infrared telescope is able to see in the spectra that our eyes can't see, and it's able to see more detail. But to operate an infrared telescope, you have to have a very cold environment. So as you can see in this picture, this drawing of the Webb telescope, you see the mirror, the large mirror, but then you can also see this sun shield. Now, this sun shield is the size of a tennis court. It's actually 5 layers of material, very thin material, that help shield the instruments from the sunlight and keep the instruments cold. So you see the mirrors of the telescope. The science instruments are tucked behind the mirrors. You have the sun shield keeping it cool, and then you have the main spacecraft bus, which is underneath it. That's the brains of the spacecraft. So the brains of the spacecraft bus is not too large. It has a communications antenna for communicating to Earth. It has solar panels for powering the telescope. Has radiators for rejecting heat from the instruments and the spacecraft itself. And it has thrusters to station keep. It's in a special orbit that Scott will talk a little bit about, but it does have to keep itself in that orbit. And so it has little thrusters, not only to get to its final destination, but to keep it in orbit. One of the main components of this telescope and testing of the telescope was the sun shield. As you can see, this is, here's a model, a scale model that they made as they were testing this telescope. These layers keep the, dispel heat. And the reason why it's layered, as heat hits the back layer, so the sun is below the telescope. As the sun warms this first layer, the heat is expelled out the side, and then out the side of the next layer, and out the side of the next layer. That's why there are 5 different layers of this heat shield. So as the heat continues to rise, it is able to be expelled out the side, so that by the time it gets to the instruments, it is still very cold. It's set to be minus 380 degrees, which is 45 Kelvin. 0 Kelvin is as cold as you can get, and not have, molecules don't move at 0 Kelvin. So getting to 45 Kelvin is an amazing achievement. So these layers are each the size of a tennis court, and they're the thickness of they're like 0.002 inches thick, so they're very thin. They're also designed to withstand micrometeorite strikes, so that if something punches a hole in one layer, it doesn't cause the tension in the whole layer to be removed. But this is the main way that it was able to cool the instruments. And here's a little video of the testing of the sun shield deployment. Now, in order to deploy this sun shield, there were 139 release mechanisms, 70 hinge assemblies, and 8 deployment molders that had to work correctly, along with 400 pulleys and 90 individual cables. And the cables, if they added up the length of the cables, they're around 1/4 mile in length. So all of these mechanical pulleys and cables and motors had to be able to deploy this sun shield and all 5 layers and tension it. They did a lot of testing of the sun shield. Frankly, when they did this test, the sun shield did not deploy correctly. They had pieces falling off, which is something that led to the delays in getting this telescope built. Of course, it was the first time a telescope like this had ever been built, and it just added to the cost, and it added to the amount of time it took to test the spacecraft. The spacecraft was not going to be circling around the Earth, as Scott will get into, so you couldn't go back up there and repair it if there was a problem. The next big part of the telescope is the mirrors. Now, in order for this telescope to fit on a rocket and be able to launch, they had to segment the mirrors, as you can see there. You can see on the side, one section of the mirrors on each side, a section of 3 on each side folded in. And you can see them practicing the deployment of these mirrors to lock those mirrors into place. Now, the mirrors, the structure of the mirrors are made out of beryllium. Now, the mirrors also have a gold coating on the surface. And they thought, wow, the gold coating, that's got to be expensive. Well, the beryllium is what was really expensive, not the gold, not the amount of gold powder they needed for them. But what they were able to do is they were able to finish these mirror segments of beryllium, take away a lot of the material, and get from 250 kilograms, which is about 551 pounds, down to 88 pounds. So each of these mirror segments are about 88 pounds of beryllium. And believe you me, they saved the dust that they shaved off of there, because that beryllium is really expensive. And the other thing is the Ball Company, the canning people, they are the ones who developed the mirror sections And not only that is the actuators on the back of the mirror. I talked about Hubble and its mirror not being correct. And there was no way to change the mirror in the Hubble telescope. So they had to change the instruments to take account for the mirror problem. On the James Webb Space Telescope, there are actuators. I think there are 7 actuators on each mirror segment, on the back of each mirror segment, to push and pull and twist the mirror segments to get them in focus. So even if the temperature fluctuates, or actually when they launched, the mirrors were deployed, they weren't exactly focused. They were able to focus the mirror by using these motors and actuators on the back of each of those sections. So that's one of the lessons they took from the Hubble problems. It's like, how can we make the changes to the mirrors to get them lined up correctly? So Ball Aerospace did that. Here you can see the first segment going into the beryllium frame of the mirror of the main mirror here. You can see there's a black a cover over the gold reflective surface there. This was November 25th of 2015 when they first started to add these mirrors in. You can see in this picture a technician helping guide this first mirror section in, and we have a little video of that of those mirrors going in. Yeah, there's 18 primary mirrors that make up the James Webb primary mirror, and that beryllium is $230 a pound. So it was $165,000 just for this beryllium framework. But they chose beryllium because it's not affected by by extreme temperatures. Again, it's getting down to within 40 degrees of 0 Kelvin. And the important thing when you have a telescope is keeping it still. So you don't want to have the frame twisting. You don't want to have to be moving those mirror sections while you're focused on observing. So that's why they chose beryllium, a material that wasn't going to be affected by that cold temperature or by the hot temperatures. And you can see here, they were able to finish those mirrors by February of 2016. They were able to get the mirror sections complete. Now, the last thing I'll talk about is the instruments. The integrated science module is a module that sits behind the mirrors, and it contains the 4 primary instruments for the Webb telescope. Scott's going to go into a little more depth on them, but there's the near cam, near spec, MIRI, and the fine guidance systems. So there are basically their images, imagers, and their spectrometers. Now, an imager will take a picture, but a spectrometer looks at looks at the spectrum of what it's looking at to be able to tell what it's made out of. Is there oxygen? Is there methane? What materials are the stars or the exoplanets or whatever it's looking at? What is it made of? They say if a picture is worth 1,000 words, a spectra is worth 1,000 pictures. So they can tell a lot more from the spectrometers that are looking at these images. The other thing about this is that all the instruments will be looking in parallel at whatever the Webb is pointing at. So it's not like you have to, okay, I've got to get the near cam looking at the image. Now I need to have MIRI. I need to put MIRI there to look. They are all looking. If this is the field of the telescope, near cam, the near spec, the find guidance systems, and everything is looking at the detail all at the same time. All the instruments are looking in parallel at the sky. The find guidance sensor is actually built by the Canadian Space Agency, and it can look at atmospheres of exoplanets, which are planets that are orbiting stars that the Webb will be looking at. Here's a picture of the near cam. It is the near infrared camera. Now, it's the primary imager on this. It produces the highest resolution images, and it's one of the instruments that helped align the mirrors when they were commissioning the telescope. It will use a wheel of filters to take different pictures of the sky, and then it can combine all those filters together to produce, for example, color pictures. So that there's a big wheel inside that instrument that turns and puts these different filters in front of the near cam. The near spec is the near infrared spectrometer. It's made by the European Space Agency as their part of their contribution to the Webb telescope. It's as I said, it's going to be able to look at the spectrum of the objects that are in the field of view. And one of the cool things about near spec is it has shutters, micro shutters, 250,000 shutters. And this is a close-up of those shutters, and they are the thickness of just a few human hairs. And so they can open and close these shutters to let in just certain parts of the star. For example, if you're looking at a star and you want to see if there are maybe some planets orbiting around it, you can have it just focus. You can have shutters closed where the star is at and be able to look. So the shutter would be closed and kind of block out that star, and it will be able to look for other objects around that star. It's amazing that these micro shutters can operate at such low temperatures. It also allows the near spec to look at 100 different targets at one time and block out, by closing the shutters, block out the field of view that you don't want to see. The other instrument that's aboard the James Webb is the MIRI, the mid-infrared instrument. It does a little bit of everything. It does a little bit that all the instrument does. It takes spectra, and it also takes pictures. And the thing about the MIRI, to be mid-infrared, it has to be even colder than the telescope. I talked about the sun shield getting things down to about 40 Kelvin. MIRI has to be down to about 7 Kelvin. So there's another cooler on the MIRI instrument. And unlike other telescopes we've launched, the Spitzer and the Herschel, they use liquid helium to keep things cool, but eventually that liquid helium would boil away and then the instrument was useless. On the James Webb telescope, MIRI has a closed loop cooling system, and we expect that it will keep this instrument to its 7 Kelvin throughout the lifetime of the mission. We don't have to worry about boiling off any kind of gases and making the instrument useless. Another thing that MIRI is going to be doing is it's going to mask stars. This is an example of masking. This is a picture of our own sun, all right, by a satellite that we have orbiting the sun, and it was able to mask out the sun. So mask, put something in front of it so that we can see, in this case, a comet streaking behind the sun, and we can see solar flares coming off the sun. When you think about looking at stars, every individual star is one of our suns, and a galaxy are thousands of our suns. And to be able to point at these stars and mask them, block them out, so that you can see other things around them, like exoplanets, is going to be very helpful in looking for exoplanets and looking at their spectra to see, is there methane in their atmosphere? Is there water on that exoplanet? But the MIRI is able to do two types of masking. Lyot masking is what we're doing here with the sun. You're putting a big object to mask the sun. In this case, in this picture, you're masking the star. But it also uses 4-quadrant phase masking to be able to get it even to block out that sun or that star with an even smaller object, so that you can see things even closer to that star. And that's called 4-quadrant phase masking, and that's something that MIRI is able to do. So a lot of technology, a lot of new technology on the Webb telescope. So here's a picture of the Webb. I said it was pretty much completed in 2016. It had its final assembly, but it went through a few more years of testing. Here they're testing it in a chamber that simulates the coldness and the heat of space to make sure everything's functioning correctly. And they had one last test last year of the deployment of the sun shield. We'll run the video here. This is the final telescope. So this was the final test. They had their fingers crossed that they weren't going to lose any pulleys or cables as they had done in earlier tests. You could see the five layers coming up and being pulled and tensioned. A lot of nerves during this final test before the spacecraft was packed up again for its trip to the launch pad. So here's a picture of it getting ready to be taken through the Panama Canal to the launch site. We have a little video of them packing it away and taking it to the ship. So we'll watch that. This was built by Northrop Grumman in California. Again, parts came from all around the world and all across the country. The spacecraft ended up going from half $500 million, $500 million budget to around $10 billion. But testing was a big part of the James Webb telescope. It's going so far away, you can't fix it. And there are so many things that could have gone wrong during the launch and deployment that if any of those things had gone wrong, you would have a useless spacecraft in orbit. So they spent many years testing it, from final assembly in 2016 to the launch in 2021. But here you can see they're going to load it up onto the ship. Not only did they load the telescope, they sent a lot of testing equipment, several semis worth of testing equipment along with it. It's in a special container that keeps the temperature at the right temperature, keeps dust from getting into the telescope. You don't want a lot of dust on the instruments there. While we're watching it load, I'll talk a little bit about the name Webb telescope. It was named in 2002 after James Webb, the first administrator of NASA during the Mercury, Gemini, and Apollo days. Scott's presentation on John Glenn, James Webb was the administrator at that time. So That is why it's named the Webb Telescope. It's named after James Webb, the first administrator of NASA. And here you see the ship arriving in South America with the Webb. It was said that they really didn't give the plan, or they didn't let a lot of people know exactly when the ship was going through the Panama Canal for security reasons. You didn't want anyone trying to take control of that ship, maybe hold the Webb at ransom. And with these days, you never know if you're going to have issues like that. So with that, I'm going to turn it over to Scott, who's going to talk about the journey from the launch pad to today.
Well, thank you, Joel. First of all, let me say that when we that was an amazing presentation. When we, at Donna's urging, decided to do a program together on the telescope, Joel volunteered. Well, I'll take the first part there about the the construction, the engineering, how it all came together, what all the parts are, and everything. And thank goodness he took care of that, because I think I'm going to have to probably rewatch Joel's presentation there about 3 or 4 more times if I'm going to fielding questions about that portion of it. But that was amazing. And again, the big takeaway is the unbelievable technology and engineering and robotics. It's just hard to even imagine that these types of things can be conceived, much less constructed and be where the Webb telescope is now. It is truly remarkable that this kind of brain power can put an instrument like this together. Again, the most complicated science instrument ever built, and it's just, and of course the largest telescope ever built, space telescope ever built. So again, the engineering, as Joel showed you, is just amazing, and that type of stuff goes on all the time at NASA. Every day, and it's what's very cool about that. So having said that, and Joel showed you all this amazing stuff, I like to watch rockets go off, so that's where I come in. That's what I like about NASA. So as Joel mentioned, we are in Kourou, French Guiana, in northeast coast of South America, and it is it's going to be Christmas Day, December 25th, 2021, as we get ready for the launch. And there we are on the launch pad. Now, the launch is being conducted by the European Space Agency. That was one of their primary efforts in this mission. Again, the entire mission was a joint effort between NASA, the ESA, the European Space Agency, and the Canadian Space Agency. So we have a launch from French Guiana that Joel's going to play for you. And we love launches. And this one now is in French. We're counting down from 10 to 1 in French. So for all you who took those high school French classes, let's see if you can count down from 10 to launch the James Webb Space Telescope, Christmas Day 2021.
Terminal count.
À tous de DDO, attention pour les décomptes finales. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And liftoff. Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
Decollage, that's liftoff in French. This is an Ariane 5 rocket. It is one of the most reliable rockets ever built. And it was actually the one rocket that met the specifications that NASA had to launch the James Webb Space Telescope. In addition, where it was launched from is on the equator, and actually the equator gives the rocket a little better push. So now we're into space animation Real fast, if you can look down the bottom there, you see a little dot moving along the trajectory line. This launch was just absolutely spot on perfect. There go the solid rocket boosters at team launch plus 2024. Just an amazing launch, totally perfect. Now you'll see down the right-hand corner there,
That was super rude.
the
of me.
fairing, that's protective covering of the telescope itself is removed, and now the telescope is exposed during the launch cycle.
Oh,
That's at about 3 minutes after launch. Now we're at the 4-minute mark, it looks like.
looking.
The first stage will cut off at
It was just a few seconds.
roughly 8:47, and there it is, some animation of
Wow.
the telescope as it looked over. It really kind of a cool concept that it's exposed like that. But just an amazing launch. And I believe what we're looking at there is perhaps the last image after launch of the telescope as it separates from the upper stage of the rocket.
And there is the view from the upper stage camera on the Ariane 5, looking at the James Webb Space Telescope. As it
And there it
moves
goes. It's on its own.
away from its launch vehicle.
That's an amazing image, and probably the last time humanity will get a look at that telescope. As Joel mentioned briefly, it's on its way, it's on its own. It's beyond human reach, and it can't be serviced, so everything has to go right.
As we marvel.
So that was the easy part, right? We've gotten through the launch, about a 27-minute launch, just an amazing job again, how it went right down the line on that launch path. Spectacular images from the upper stage of the Ariane 5 rocket.
Operations manager of the Space Telescope Science Institute, Carl Starr, who will be calling out the procedures that will lead to the deployment of Webb's solar array.
It immediately, very quickly, you'll see it's deploying a solar array very quickly after it leaves the upper stage.
Down in the fishbowl where there is jubilation, let's go to Raphael Chevrier of Ariane Spas.
Now we get into what's called the, as some lovingly called it, is the 31 days of terror. If you look on the right-hand side, this is all that goes on along for 30 days as the rocket, as the telescope, excuse me, begins 344 mechanical and robotic moves that all have to work. If one doesn't work, the telescope never works. If you look along on the right-hand side there at the bottom, it'll explain and show when the move is being made and what is being done. And you'll notice there on day 29 was the burn the engine burn that took the telescope to the Lagrange point, L2 it's called, a little sweet spot in space where it sits. So every one of those 344 mechanical moves, robotic moves, all had to work perfectly. And as we said, unlike Hubble, it's out of reach. It's on its own. There was nothing that NASA or the European Space Agency could do if one of those moves didn't work, and that's why they lovingly referred to it as the 30 days of terror. So we've launched, we've completed the deployment process, and now we come to what's called commissioning. And Joel mentioned the 4 main instruments that are involved, and there they are again: NIRCam, NIRSPEC, the Fine Guidance System, and MIRI. So what happens during the commissioning process is the Webb has 4 science instruments on board. Each has multiple modes of operation, which need to be tested, calibrated, and verified before they can begin to conduct science. Each instrument, as Joel touched on, is highly sophisticated set of detectors equipped with unique lenses, masks, filters, customized equipment that allows it to perform its science. So over 2 months now, after deployment, they go through what's called the commissioning process, where they test each and every one of these instruments. They're configured and operated in various combinations to confirm readiness for scientists. This is being conducted from the ground at the Goddard Space Flight Center, the Johns Hopkins Applied Physics Lab, the European Space Agency, Space Telescope Institute, and many others to complete the commissioning. In other words, they're going through all 4 science instruments, running it through tests, calibrating it, setting it all up, so everything works as Joel described how it should work in the beginning with those 4 main instruments. It took about 180 days to complete this, and at this point, James Webb is ready to do the science. So why the James Webb Telescope? What is the science? On January 24th, 2022, the telescope arrives at a spot in space called the Lagrange point. I just saw a small question pop up. Where is that at? The Lagrange point is 1 million miles approximately from Earth. As Joel mentioned, that this telescope orbits the sun, unlike the Hubble, which orbits the Earth. The telescope sits opposite, if I get this right, it sits opposite the Earth to where the sun is. In other words, it's on the other side of the Earth, with the Earth between the sun and the telescope. Now, how did they decide who gets to use the telescope? The Space Telescope Institute in Baltimore, Maryland, in coordination with NASA, leads a process that has selected the astronomers and scientists who've been awarded time with a telescope for astronomical study and science. The application process, which was cutthroat at times, as you can imagine, was conducted in what's called a dual anonymous way. That is, the selection panel saw in the application, all that they saw in the application, was the science, not who submitted the application. In the first go around, 1,173 applications for time with Webb were submitted, and 1/4 of those were selected. In the end, the Institute was looking for the most interesting and transformational science that could forever change our view of the universe. Again, as we've said, the telescope is the most complicated science experiment ever built. So what is the science? Of course, it's impossible to predict what will be seen, what may be discovered, but NASA had 4 main areas that they would like Webb to look at. The first is first light in the universe, as Joel's putting up a picture there. The telescope is a wonder of engineering, as we've described it. It's going to reveal the deepest image of our universe ever taken, some of the very first light in history. Webb will not see the beginnings of the universe, but it will see periods of the universe that history has never seen before. Specifically, scientists want to see the first objects formed as the universe cooled down after the Big Bang. Second, they're looking at the assembly of galaxies in the early universe. Webb will be able to see distant galaxies because of its enormous primary mirror that Joel showed you, and instruments that focus on, again, as he discussed, infrared light, allowing it to peer clearly through dust and gas. Scientists will study what are known as the local group of galaxies, a cluster of 20 galaxies within a diameter of approximately 10 million light years, which by the way is considered close by astronomical standards. Third, the Webb telescope would be looking at the birth of stars. How are stars born? What happens to a star throughout its life? And how does the death of a star affect the universe around it? Scientists believe the elements of life were first produced in the first generations of stars after the Big Bang. By stirring up everything and producing chemical elements, our little planet Earth came to be able to support life. So scientists need to measure what happens at the beginning of stars to understand how that came to be. And lastly, exoplanets and protoplanets. Simply put, exoplanets and protoplanets are planets not in our solar system, with protoplanets being much smaller. Every star in every galaxy in the universe has at least one planet, which means there are most likely billions of exoplanets. Webb will look for the chemistry and conditions for life on exoplanets, or as it is known, the Goldilocks zone. Not too hot, not too cold. The James Webb Telescope will be the premier observatory over the next decade and beyond, serving thousands of astronomers worldwide. It will study every phase of the history of our universe. So why Webb? Much of what will be seen, we will not understand. But that's the definition of wonder. The reason for exploration and discovery. The reason for NASA and the international space community. We do it, as someone once said, to perhaps end our cosmic loneliness, and to answer the question, is there life out there? So I'm going to let Joel show these last few slides here, and then we'll hopefully get to some questions and answers.
Thanks, Scott. Nice job with that. So this is a selfie of the Webb telescope. So after all the mirror sections were deployed, there was a camera that was able to take a picture of the mirror section. So this is actually a picture of the different mirror sections, but they haven't been aligned yet. But on the right, this is after all of those actuators on the bottom of the panels aligned the mirrors, so they were all pointing at the same pinpoint of light. And so this is, you know, we saw that view of the Webb leaving the rocket stage. Well, this is a selfie from Webb before it actually started producing science. And just probably an hour ago, I'm sure the president didn't realize that Scott and I and Donna were doing a presentation here, but they decided to do a presentation, and they released the first image from the Webb. Gave us a sneak peek tonight, and you are seeing the first image from the Webb. As the administrator of NASA said, if you had a grain of sand and you held it out on your finger at arm's length, this would be the area of the universe that this little snapshot was taking. And when you look at this picture, there are a few stars, but most of what you are seeing, all the smudges, all the little smudges, these are galaxies. So these are thousands of stars. And it's intercepting this light about 13 billion years out before it even would reach us on Earth. So, you know, as Scott talked about planets being around these stars, think of all of the suns that are in these galaxies and all the planets that could be around these suns. The Webb will be able to look for those exoplanets and those protoplanets and you know, perhaps tell us, are there a lot of planets with water? Are there planets with methane in the atmosphere? Could there be life on some of these planets so far away? Was there life in the past, or could there be life in the future? We don't know, but these are amazing. You know, when Edwin Hubble, the Hubble telescope, the Hubble Space Telescope, which is still operating, by the way, after over 20 years, when he was an astronomer at that time, they didn't realize that these blobs these smudges were actually galaxies of stars, so a lot, we have learned a lot in just the last 150 years of exploration. I'm sure the Webb will teach us much more in its at least 5 to 10 year life span here. So this is the first image released from the Webb. There will be more images released and spectra released tomorrow. So the release was actually at 5:30 p.m. today, but tomorrow, starting, I think it's at 9:30 Central Time, they were actually going to start releasing images out on the NASA. This is nasa.gov Webb first images. So that would be a good spot to go tomorrow morning to see the first images released from the Webb Space Telescope, as all those scientists who have proposed looking at objects in the universe get to start seeing the science produced by this telescope. So with that, we are open to questions.
Thank you, Joel, and thank you, Scott. I see we have a few things in the chat. Are you watching these two? We have a question from John. How far is L2 from Earth? Could one of you answer that?
And I think Scott said about 1 million miles.
About 1 million, right, 1 million miles. Yep.
So let me go back and our images and show you. There's certain,
There you go.
Yeah, there's certain points where the sun and the moon and the Earth balance, all their gravity balances each other out. These are called Lagrange points. And so what you can do is you can send a spacecraft to a Lagrange point, and it goes into what's called a halo orbit. So imagine it's an orbit. It's not just one little point. There's a lot of spacecraft at L2, for example, but they orbit around this little point and pretty much stay there. You don't have to use a lot of fuel to stay in orbit. When you're orbiting the Earth, like the space station that's orbiting the Earth, it's always being pulled down by gravity towards the Earth. So you always have to boost the space station up a little bit. It takes rocket power to boost the space station up all the time. If you're in a halo orbit, the closer you can get to orbiting that exact spot, the fewer boosts you have to do. And that's what's going to limit the James Webb Telescope's life. It's not going to be the coolant. We talked about how it doesn't run out of coolant to keep the infrared cameras cool. What's going to limit the Webb is its maneuvering fuel, because one thing about a telescope, you have to point very precisely, which is what you use those fine guidance sensors for, and you have to hold that position. And that was some of the amazing technology, frankly, in the Hubble telescope, was just those guidance sensors keeping it steady. Same thing in the Webb. You've got to keep it steady. So there are little thrusters on the Webb telescope that keeps it steady, keeps it pointed, and that's what's going to limit the life. We think we had a great ride up on the Ariane 5 rocket. It got us into orbit where we didn't have to use a lot of fuel to get out to L2. So we're pretty sure we can make it 5 to 10 years on the fuel, and probably as they conserve fuel, probably even longer, have a longer lifespan for the Webb. Interesting, we're also planning to put a little space station at the Lagrange point around the moon to actually send astronauts to and from the moon from that Lagrange point. So again, the Lagrange point, it's huge. There's a lot of area there, but you're orbiting a point where you don't have to spend a lot of fuel to stay in that orbit. And that's why they chose L2 to put the Webb telescope there.
Okay, excellent. That clarifies for us. I had forgotten, I read an article from the astrophysicist Jane Riley, I think it was, who was interviewed by Scientific American. What is the fuel that's operating this energy to keep going for 5 to 10 years? What is the fuel?
Well, it's usually hydrazine. It's a simple fuel where for the thrusters, you just have to put the fuel together and they will thrust, so you don't really have to ignite. So it's I believe it is hydrazine that they're using. That's what most thruster systems use.
Okay, we have another question from John. What were some of the experiments that were accepted for time from the Webb?
I would just mention that I can't directly answer that other than a lot of deep space experiments, but it should also be noted that the Webb will also be looking at things in our own solar system. That's not to be forgotten. Some of the applications that were accepted are studying like the moons of Jupiter and a lot of things going on in our solar system. There's still so many unanswered questions there. So it's not simply a deep space look. It's also looking at things, as I said, in our solar system. But again, they had identified the 4 main things. Scientists are very excited about the exoplanets. They really believe that there is potential for discovering and looking at life in those areas. But it's not to be forgotten that they also will be studying our own backyard here.
Yeah, they may be able to spot other objects out beyond Pluto in our own solar system that are, a lot of those objects out there are very dark. Now they're so far away from our star, our sun, that they don't reflect. They're not getting a lot of light on them to reflect, and they're pretty much made of rocky, dark material anyway, so they don't really reflect a lot. But you have a lot of light gathering capability in the Webb, so the chances are we could identify a lot more objects out in the Kuiper belt, which is the area beyond Neptune, where Pluto's located, and even maybe even in the Oort cloud, which is theorized as the cloud of objects even further out that encompasses our solar system. One thing I will mention, the United States took most of the budget for this Webb. In 2011, the Congress considered canceling the program because of the cost overruns. There was a huge outcry. There were pros and cons. There were some saying that the telescope that ate the astronomy budget, because a lot of other programs had to be curtailed or delayed to help pay for the cost increases on the Webb telescope. So it helped that other countries were participating too. And what they usually do is they give a percentage of the time. So Europe provided the launch vehicle and they provided some of the instruments, so they get a percentage of the time. The scientists from Europe, Canada provided an instrument, so they get a small percentage of the time. So they also typically, if we look back at Hubble and its over 20 years lifetime, they at a certain point they will open it up and even give amateur astronomers a chance to propose a target for the Webb to look at, and that will be based on its merits, on scientific merits. But Scott is exactly right. We're going to look at inward at our solar system too, and be able to discover a lot. I know that Neptune is a planet that they really want to look closely at, and will use the Webb to do that.
Okay, I'm excited that the Hubble could be opened up to amateurs. That's just so exciting. So democratic, right? Pete asks, what temperature are the science instruments operating at? And I know you mentioned some ridiculously cold number earlier, but could you run us through it if there's any that we didn't discuss?
it's interesting. So the sun shield gets the instruments to 40 degrees Kelvin. And again, 0 Kelvin, at 0 Kelvin, your molecules aren't moving. Atoms aren't, the molecules and atoms aren't moving at 0. The MIRI goes down to 6 Kelvin. So very cold temperatures. An interesting story, all of these instruments had heaters on them. And even after the sun shield was deployed and they started to cool the Webb telescope, they kept the heaters on. It's like, well, why would you have heaters on if you want to get the instruments cold, right? Well, all materials from Earth have a certain amount of water vapor locked into them. And the reason they had heaters is they wanted to get rid of that water vapor as it outgassed from that beryllium and the rest of the structure of this spacecraft. So they used heaters even after the sun shield was deployed for a while, until they felt they were at a point where either all the water had outgassed or was locked within the structure. And then they turned the heaters off, and then they let those instruments really cool down. Because if they hadn't done that, they would have had a chance that ice would have formed over some of the instruments, and that wouldn't have been a good situation too. So that's why there were heaters on the instruments. But at this point, after these 6 months, we are down to 40 degrees Kelvin. And again, the MIRI is even cooler, or I'm sorry, the NIRCam is even cooler, down to that 6-7 degrees Kelvin, to be able to see in that near infrared wavelength. And that's, again, we've had the Spitzer telescope be able to view objects like that, but it was limited by the coolant that it had with it that eventually got too warm and boiled off. We won't have that worry with the Webb.
Linda asks, is there a reason for the honeycomb shape of the mirror?
Yeah, the reason the structure was honeycomb was to save weight. When they first proposed, here, I'll go back to a picture of it here. When they first proposed building the Webb, and they wanted to get it out to L2, they had a lot of things they had to deal with. One is, how do you send a big mirror out there? And they decided, well, we can fold it into sections. How do you cool it? Well, we can have a heat shield, sun shield that folds or it's deployed. But the other thing is, you had to worry about weight. If they hadn't made this into a honeycomb, it would have been too heavy, either too heavy to get there, or it would take so much fuel, you wouldn't have much fuel to last more than maybe 5 years, as just to get there into orbit and to keep yourself there. So they were able to get rid of 90% of the material by making that honeycomb structure. The biggest reason is just for the decrease in the weight, because again, your rocket can only lift a certain amount, and the less you need for the structure, the more you can add to the science.
Wow.
Good question though.
Yes.
And it's amazing to me that the canning company, Bell, it's the ones who put this very advanced system together.
That is very exciting. Is it regarding the mirrors, Joel? Beryllium, had it been used in other spacecraft, in other mirrors, or was this the first time?
I am not sure if it had been used before, but I'm sure that this was the largest application of using beryllium. It's very expensive. It's an expensive material. Again, when they talked about how they gold plated the mirrors, and the people, the first thought is, well, gold plated, how expensive was that to have these gold I can get to a picture. How expensive to put gold on these reflective surfaces, but the gold was nothing compared to the beryllium, because it only needed a small amount of gold across the surface of the mirror there. So again, I'm not sure. I'm sure it's the largest application of beryllium. Even on Earth, some of the great telescopes on Earth, the more modern ones, use segmented mirrors. It's as you build a mirror for a telescope, you have to worry on Earth about sagging because of the weight. You have to have a certain curvature for that mirror. So a lot of the large telescopes that are built now are segmented, and they do have actuators on the bottom of those segments to push and pull. But on Earth, they push and pull the segments of the mirror to make up for the atmosphere changes. So they have computers that can look at the atmosphere changing, and it can change the shape of the mirror to make up for the atmosphere changing and give you a more sharp picture. A lot of the telescopes on Earth now are close to what Hubble can do as far as resolution and clarity, just based on the software that we can use now and changing those mirrors a little bit to make up for the atmosphere. But Webb will exceed everything again. And Webb is, I think probably the next type of telescope might be a large, imagine a large reflector in a crater on the backside of the moon. That will probably be, if you could put something in the middle of the big crater and pull it out, you could have a large reflecting surface there on the back side of the moon. You don't have to worry about any stray things, and certainly you could keep it very cold there. That will probably be something we will do in the future. It's already being talked about now. But the Webb, there will be nothing comparable to the Webb for many years.
This whole thing has been so exciting. I'm sitting here grinning just with the prospect of how great this is and how there's already a future thinking about another telescope. It's so exciting. We have another question from Janet. What happens once the Webb becomes non-functional?
Well,
Joe, will it
ahead,
just be,
Scott.
will it, because of its position, will it be simply space debris, or do you believe?
It'll stay in that L2
Right.
until it will eventually drift away from L2 and just orbit the sun. It will be pulled by the sun's gravity, and will orbit the sun, just like as we've launched spacecraft to the moon. Even some of the Apollo stages, every once in a while you'll hear about astronomers detecting something headed towards Earth, and they'll look at it and they'll look at the spectra. We talked about spectra and being able to tell what it's made of. Well, we would get the spectra back and say, well, this is aluminum. Well, what we would find are stages of the Saturn V, like the third stage that got them to the moon, orbiting the sun and eventually coming back close to the Earth, but then going back and orbiting the sun. So I think eventually the James Webb Telescope will become space debris orbiting the sun, just like that red Tesla that SpaceX launched towards Mars a few years ago. One other thing I will mention, one of the news reports a few months ago was that the Webb telescope, one of the mirrors, had gotten hit by a micrometeorite. There's still micrometeorites in space, and striking the moon, and it actually struck one of the mirrors. We don't think it made much of a difference, and the spacecraft is built to be able to withstand slight blemishes in those mirrors if it gets hit by material. It's certainly not as much danger, I would say, as the Hubble, which is an Earth orbit, which could be struck by paint chips from satellites and things like that. But it is, Webb will be struck by objects, hopefully not enough to damage it where it can't return science.
Right, and kind of related to the question, for example, the International Space Station, it's set to be decommissioned, I believe, around 2031, I think, is what I've heard, and that'll simply be brought back down to Earth since it's within the pull of the Earth, and they're going to crash that into a sweet spot in the ocean somewhere where it won't bother any coral reefs or things like that. But so there's different things they can do with these things, but Webb is going to be way out there. And as Joel described, that's probably the fate. But we got a long way to, we're just getting started and they're already wondering how we're going to get rid of this thing, Joel.
Well, you know, it's funny, originally the Hubble was going to be brought back by a space shuttle, and the Smithsonian had dibs on displaying the Hubble telescope. But, you know, after the Challenger accident, we started thinking about that. Is it really worth risking a crew to go up and just to get this Hubble telescope at a certain point? So the Hubble, just like the space station, will eventually be brought back. We will probably launch a little robotic rocket to attach to the Hubble. One of the things we put on the Hubble on the last servicing mission was a docking ring where we could send a robot up there to latch on and then use rocket engines to control the descent down to the ocean, so it doesn't damage, you know, accidentally fall somewhere where we don't want it and damage. There was talk when the Webb was being built, there was talk about putting a docking ring on the Webb just in case something didn't unfold correctly. Maybe we would have the capability to get out there. Right now, we don't have the capability to get out there to the Lagrange point. In a few years, we're getting ready to launch the Space Launch System in late August or September. It's unmanned, but it's going to send a space capsule, the Orion space capsule, around the moon. And then the next launch of that SLS will send a crew around the moon. So we might have the ability to reach the Webb if we wanted to, but you probably do more damage probably getting close to it than you would do any good. But thankfully the Hubble was built to be serviced by the space shuttle. Unfortunately, we don't have our truck anymore to go pick up satellites and work on them.
That is just amazing in and of itself. Just so that I can use my imagination, how big is a micrometeor and how fast is it traveling when it makes impact with the Webb mirror?
Well, they can really, all it takes is something the size of a dust particle to hit you, and it's traveling. I don't know the exact speed it's traveling, but traveling pretty fast enough to puncture a hole in objects. You know, the space station often has to be moved for large objects. The Air Force tracks objects in Earth orbit. They can track things down to about the size of a bolt, but anything smaller than that we can't track. And so the space station and the space shuttle, for that matter, has been hit many times by objects. There was on the space shuttle once when they landed, they noticed on the windshield, one of the windshields of the space shuttle, an indentation, and they looked at what caused it. It was a piece of paint from the second stage of a rocket that had hit the space shuttle. Now, luckily, the space shuttle had several panes of glass and it was able to withstand that. But if you ever get down to the Kennedy Space Center in Florida and you see the Space Shuttle Atlantis on display, they have the payload bay open, and you can walk and you can see where they've actually made repairs as things have punctured those radiators on the space shuttle. Luckily, not damaging any of the coolant loops, but you could see where they have had to make repairs because of things like that. So it was interesting. I don't think any of us expected a micrometeorite to hit Webb so quick, But it just show you that, there's not a bunch of emptiness out in space. There's a lot of dust and particles. And really, we're not talking about a rock. I guess there could be a rock size object that hit, but even smaller than that. Very small particles going at high speed can cause damage. If you had an astronaut in a spacesuit out there, it wouldn't be a good day if they got hit by that.
Yes, that's right. I have one last question for you, and this is mine. When I saw that Goddard Space Flight Center in Maryland was the lead in the development of the Webb telescope. But when I think of Goddard, I often think of Earth science with projects like global precipitation measurement and others like Aqua and Aura and Calypso, always looking at climate and weather on the Earth. How did Goddard take the lead with the James Webb, a telescope that looks out as far as we ever have looked?
Well, I think where it comes from is that Goddard partnered with Johns Hopkins University for the Hubble telescope. Goddard has been the center for Earth orbiting satellites. You are correct. They sort of handle the missions that look back at the Earth. The fact that the Hubble orbited the Earth gave them some experience with monitoring and taking care of spacecraft, because these spacecraft aren't autonomous. They have people on Earth checking to make sure the systems are running right, troubleshooting when there's problems. They have some autonomy. If the Hubble or the Webb was to be hit by something that knocked it out of place, where it lost track of where the sun is, for example, it would go into what they call safe mode, which is okay, switch from my high gain antenna to my low gain antenna, and don't do anything crazy. Don't use all my fuel right now, just because I don't know where I am. Call Earth, see if they can help me. So there is some autonomy built into our spacecraft. But Goddard has taken the lead on Hubble, and I think because of their experience with Hubble, it made sense for the next telescope that's replacing Hubble to be handled by that same Johns Hopkins group and Goddard Space Flight Center. So that is probably the reason. Although a lot of the NASA centers, lended their expertise. I know Marshall Space Flight Center did some testing as they did some testing on the parts for this Webb, and I know a lot of the NASA centers have contributed to the instruments and the technology there. But I think it's probably because of their lineage with Earth satellites and the Hubble that they would be the natural to follow up with the Webb.
Sounds like it. Thank you. I don't see any more questions. So I think we're done. I want to say to both of you, as well as our audience, we were watching lag time on the internet just in general, and I think everybody is going on to NASA sites or the European Space Agency or the Canadian Space Agency, because the internet is really, really bogged down right now. So if there was any delay in our program, I hope everyone will understand that. It was fine with us, but we know that there were delays. In the meantime, thank you to our audience for attending. Our audience tonight represents locations from all across America and all across Canada and the nations in Europe, Africa, South Asia, and Oceania. Knowing the time differences, we very much appreciate everyone's interest. I hope all of you have enjoyed the program, and we will be watching the release of the first images from the James Webb Space Telescope tomorrow on our NASA TV, and for the rest of the world, the Canadian Space Agency and the European Space Agency. please mark your calendar for Scott's next virtual Zoom program on Tuesday, July 19th at 6 p.m. our Central Time. Godspeed, John Glenn. And to our audience, please complete the short pop-up survey that will appear when we close the Zoom connection. As always, we value your input. Joel and Scott, this was a tremendous presentation. I'm so excited. I'm sure that we'll all have questions afterwards. We will have a recording of this program posted by tomorrow for everyone's use. If anyone did have trouble logging on, it will be there again for you tomorrow. And now I'd like to turn it back over to Joel and Scott for your closing comments. Scott?
Well, again, thank you, Donna and Joel. I sure learned a lot from Joel today, that's for sure. It was wonderful. You know, I just wanted to add one more thing about James Webb himself. Joel mentioned he was the administrator from 1960. I believe he retired shortly before the moonwalk. But at heart, James Webb wasn't really a rocket man. He was more of a scientist. And early on, he did envision these large space telescopes as a way to see the universe. And I think that went a long way toward NASA naming the telescope after Mr. Webb. So if you read a lot of the older NASA books like I do, he's prominent in those books, but it obviously was well deserved that the telescope was named after him. So thanks for everybody listening on my end, and I really appreciate it. And as always, with everything I do in the Solar System Ambassador Program, I learned a lot tonight, and that's the best part.
Great. And Joel, your thoughts?
Well, it's amazing that after all of these years that the telescope wasn't canceled, and that all the testing was, all the testing they did worked, because it was almost a flawless deployment. All these things that had to go right, they talk about every time they don't launch a rocket, people complain, you're not launching it. But if once that rocket launches, you don't hear anything about it anymore. But if that rocket blows up on the pad, you hear about it. It's like, why did they do that? Why didn't they test more? So the delay and the cost for the James Webb Space Telescope was really down to the testing. We always at NASA, they always try to have the best technology, cutting edge. We couldn't do anything like the James Webb when the Hubble was designed. Couldn't do anything close to what James Webb is going to be able to do. Hubble's still operating. Hubble has been amazing. It's still operating. It's great that we're going to be able to use the Hubble and Webb. Hubble might find something that then they will point the Webb at. It's amazing how technology's improved. It is amazing that we even got off the Earth in one piece. You never know until you launch whether the launch is going to be successful. But everything went right. All of the commissioning went right. We're going to start really seeing the science now. We're going to get some amazing pictures and amazing spectra from this James Webb telescope for the next 10 plus years. And so be watching the web for updates on at nasa.gov, updates on the science that Webb is able to bring us. It's a pleasure talking to everybody today. Again, hope to see you all in person someday.
Thank you, Joel, and thank you, Scott. And again, thank you to our audience. We'll see you next time. Good night.